Good morning, children. How are you today? I hope you are all safe in your respective houses. Observe minimum health standards to avoid catching COVID-19. Today we will discuss another lesson entitled The Fundamental Theorem of Calculus. For our objectives, so at the end of the lesson, you will be able to illustrate the fundamental theorem of calculus, compute the definite integral using the fundamental theorem of calculus. So in the past lessons, you will see that the only similarity between definite and indefinite integrals is their use of the notation integrand, or the S-like symbol. The indefinite integral is the inverse of differentiation, while the definite integrals is the process of finding the area of a plane region by taking the limit of a sum. So the only vague connection we have established is the relationship between the antiderivative of a function and the area of the region below its curve. So let's try to observe the graph. So what are the boundaries of the shaded region? Okay, so the connection lies in the powerful result which forms the basis of the theory of the Riemann integration, or the fundamental theorem of calculus. It stresses the inverse relationship between differentiation and integration. Very loosely, the theorem says that the integral of the derivative of a function returns the same function. Okay, so let's now find the boundaries of the shaded region. So from the top, we have the function f of x. From the bottom, we have y is equal to 0, or the x-axis. From the left, we have x equals 0, or the y-axis. And from the right, we have x is equal to 3. Now, in the Riemann sums, we need to approximate the area of these squares. So we have to add all the areas of these rectangles created. So that is for the Riemann sums. Now, for the fundamental theorem of calculus, we will not be using addition of all areas of these small rectangles. So let's go to the definition of the fundamental theorem of calculus. So let f be a continuous function on the interval a to b, and let uppercase f be an antiderivative of the function f. That is, the derivative of the uppercase x is equal to the function f of x. Then we have this notation. The integral of the function f of x dx from a to b is equal to the is equal to the evaluated function of the uppercase f of b minus the uppercase of f of a. Okay, so we will use the vertical bar notation. So we adopt the following notation. The uppercase f x evaluated from a to b is just equal to the value of our uppercase f evaluated in b minus the value of our uppercase f evaluated in a. So using the above notation, the FTOC now states if the uppercase f is an antiderivative of the function f, then we will have this notation. So now let's take an example. Find the exact value of the integral of the quantity 3x plus 1 dx from 1 to 2 using FTOC, or the fundamental theorem of calculus. So we have our solution. Note that the function f of x is this one, 3x plus 1. Then the antiderivative of the function is the uppercase f of x is equal to 3x squared over 2 plus x. So by fundamental theorem of calculus, we have this one. So observe that if our antiderivative has more than one term, we shall enclose this one with the parenthesis before we put a vertical bar evaluated from 1 to 2. Okay? So let's now apply the fundamental theorem of calculus. So we will get this expression. So all x's of this antiderivative will be replaced by the upper boundary and minus the evaluated antiderivative using the lower boundary. Okay, so moving on. So let's simplify our equation or our solution. So we have 8 minus 5 halves. This is 2 squared is 4 times 3 is 12 divided by 2 is 6 plus 2, that is 8. Then 1 squared times 3 is 3 divided by 2 plus 1 will give us 5 halves. So simplifying, we have 11 over 2. So that is 2 times 8 is 16 minus 5 is 11 divided by 2. Okay, so let's have another example. So find the exact value of the quantity 3x, the integral of the quantity 3x squared minus 2 dx from negative 1 to 3 using FTOC. So for our solution, so we have the integral of 3x squared minus 2 dx from negative 1 to 3 is equal to the antiderivative, which is x cubed minus 2x, evaluated from negative 1 to 3. So applying the FTOC, we have replaced the upper boundary, or replaced the x with the upper boundary, 3 minus, okay, so we replace also the x with the lower boundary. So we get, simplifying, we get 21 minus 1. So 3 cubed is 27 minus 6 is 21. Then we have cube of negative 1 is negative 1. Then negative 2 times negative 1 is positive 2. So negative 1 plus 2 is 1, since we have 1. So 21 minus 1, that is 20. So I'll give you 10 minutes to find the answers of this one. You may pause this video and solve, then play to check your answer. Okay, so time is up. Check your work. So the answer for problem number 1 is 6, and for problem number 2 is negative 18. So how among you have the correct answer, or hoping that you get the correct answer? Now for our evaluation, answer the learning activity sheet number 4, quarter 4, week 5. And for your assignment, answer the learning activity sheet number 1, quarter 4, week 6. And thank you for watching. Have a nice day and stay safe.